Hello, so today we're going to talk about fluids. Well, if you think about fluids, is it just a liquid? Well, it can be a liquid like water, but it can be a gas. But some fluids you can't drink it like water. But some fluids like mercury, you cannot drink it, isn't it? Well, I think, Archimedes from the ancient Greece discovered that, if you came into the water and you push the water will also push you. So we need some letters to come up. Let's say the water's density is rho. Okay? So then, G is the gravitational force, 9.8066. And V is the volume of a person, and M is the mass of a person. So this comes in kilogram divided by meter squared. This comes to this is constant. This comes to meter squared. Then this comes to kilograms. And the first thing that everybody knows is the really fun equation known as rho equals V over M, or M over V. Okay, so from this equation, not from this equation, but the thing that Archimedes got out of his bath and said Eureka with none of his clothes, we can turn out that, okay, so let's say this is a person, this is a lake, and this is a person, okay? So let's say, by calculations, we can know that this bit of the volume comes to 0.1 of the volume of the person, and this one comes to 0.9. Now, what if the person's force to come here, or the buoyancy? Well, the buoyancy V is 0.9 rho of the water, so let's say like this, times the G times V. So if you do that with this, we can learn a pretty nice thing, that if the density is 0.1, then the person is 0.1 dip down, which means that person is like this. This is 0.1 and this is 0.9. We can notice by the famous Tilling. The Tilling, who says, in a lake, a person is only showing his head. Well, I have made up that Tilling, but have you ever wondered that this is a sea? Well, I guess I should call it a sea blue. And this is iceberg. But how many? What is the volume? Well, we can easily work out, because the density of the ice is 0.9 of density of the water. So we can learn that 90% of the iceberg is below seawater. Well, that's a pretty interesting fact. But in the 1630s, a Switzerland person, not a person actually, it's a family, the Bernoulli family, discovered a pretty nice fact known as the Bernoulli principle. They have discovered that, it is like in science, well, this comes out to the leading. Well, this is not steady. This is when Newton came out. Well, Bernoulli is a little strange. It comes out that the pressure plus rho GH. Well, you can already know that these are a little simple. And what about these? Okay, so why is it? Well, let's prove the Bernoulli equation. What we need to think is this. We have a little thing. Okay? So this thing is this thing has fluid in it, but not, well, the fluids are like water. If you move it somehow, it will come out another way. Like if you drink in the water, it'll come out of the, it'll come out and go to the lung. Oh, sorry, not the lung. Go to guts. So let's prove the equation. Okay, so let's say the density of this water, this fluid is rho. Okay, so this is A1 and this is A2. Well, the A1 and A2 are the areas, and the fluid comes in A1 V1, and in A2 it is V2, and the pressure is P1 and this is P2. Okay, so let's say in the small time, which is we'll now call as delta T. Okay, so when how can I call it? When the fluid comes to this point A to this point B, well, delta multiplied, well, this, you know, this, well, this is actually like a piston. So the piston's width, I should call it, well, this is delta x1, and well, so we can call it that delta x1 is this v1 delta t, and delta x2 is v2 delta t. Okay? Yeah, you got it. So Bernoulli had a lot of things known as, well, the Bernoulli's principle, and according to him, it said that delta v equals a1 delta x1 equals a2 delta x2. Okay, got it. So okay, so the force F1, okay, the force F1 going to the piston A1. Well, that the force is F1 equals A1 P1, and A21 is P2, A2 is F2. So these forces gave up some energy and some work. So the work is equal to F1 delta x1, because the formula work equals F times S. Well, S is the distance you had in this time delta x1. So, but this is also answer to P1 A1 delta x1, because F1 is P1 A1. But this also turns out to be delta V. So we got it that this equals P1 delta V. Let's talk about in the next page. Okay, so the force F2. So let's have the diagram again. Okay, so this is F1. This is piston. So this is F1. But we can have another force that is not, well, this is not cooperation to F2. Okay, so this one we can have -1. Okay, so this equals minus P delta V, as we did it in the last page. So the thing that, okay, so the work, all of the work coming out to be the sigma of the work, which turns out to be P1 minus P2 V. So, and the delta T will, in time delta T, the volume of the fluid is delta V, and the mass delta M is rho delta V. Okay, so the time delta T, the kinetic energy, so EK equals half mv to well, this is, well, if you do that, it comes to this one. And if you do it again, and well, do the potential energy, if you all do that, and if you get the equation delta work is equal to delta EK plus delta EP, you get the Bernoulli equation. Whoa, what a lot. This is the Bernoulli equation. Thanks for watching, guys, because well, this video, I was trying to upload a video about integrals, okay? Well, like this one and dx. But unfortunately, the book I was working to make a video about integrals has gone. So I have spent the next 3 weeks to find that book. But I guess it came to the rubbish pile. So unfortunately, I have had to upload this video. Anyways, thank you for watching this video. Please subscribe us, and if you leave a comment, I will try to upload a video about that. Thank you for watching. Bye.